Okay, so this is the 2023 Higher Level Leaving Cert Maths Paper 1, question 4. Now this is a complex number type question. So in part A we have the complex number z1 is equal to 1 plus I. It's the root of this quadratic complex equation here. Find the value of p where p is a plus bi and a and b are elements of z. Okay, so there are a couple of ways of doing this, and I might do them both ways. The first way I'm going to do it is to look at the product and the sum of roots method. So if you remember from algebra, we had quadratic equations will look like this. So they'll look like x squared minus if you add the roots here, multiply by x, and then multiply the roots here. So it's the same with complex numbers. So we can say here that we have z squared minus, we have two roots in here that we have to add. Let's call them z1 and z2, which we're adding. And this is our x equivalent here, if you like. And then we've got to multiply them out here. So this is where the p was, if you like. So this is where we have to multiply them. So it's z1 times z2, and that's equal to 0. Now we do know that one of our roots is 1 plus I, so that's going to be handy here. Remember, our complex quadratic equation is z squared plus 3 minus 2i times z plus p is equal to 0. So what we can do here is equate these and these here. Now we know that if we take this here and just slot in one of our roots, we have z squared minus, one of our roots is 1 plus I, so we can say 1 plus I here. We have to find the second root, that's our z2, z here, and then we have 1 plus I here again, multiplied by z2, and that's equal to 0. So let's see if we can find z2 here first. We can equate these here anyway. So in other words, we can say 3 minus 2i is going to be equal to minus 1 plus I plus z2. So that will give me 3 minus 2i is equal to minus 1 minus I minus z2. And that will give me minus z2 is equal to 4. Let's see, minus I, if we bring these two over to the other side. So that'll give me my z2 then, or the second root of this quadratic, complex quadratic here, is minus 4 plus I. Okay, so once we have our second root here, we can use this part here. We can use this part here, if you like, or in this case, this part here. So we know that p is going to be equal to 1 plus I times z2. We now know what our z2 is. It's minus 4 plus I. So let's just multiply that out. So it's 1 times minus 4 is minus 4 plus I minus 4i plus I squared. That'll give me a value for p of, let me see, we have minus 4. This here is minus 1, so that's going to give me minus 5. And then we have plus I minus 4i, that's minus 3i. So there's my value for p there, minus 5 minus 3i. So that's kind of a long-winded way of doing it. Let's do it maybe a shorter way. Let's see, if we know that z1 is equal to 1 plus I is a root, that means if we substitute that in here for z, we should get 0. So let's do that. So we'll do that here. So we have, our original equation was z squared plus 3 minus 2i times z plus p is equal to 0. So remember, this is the second way of doing it here. So we can substitute in 1 plus I for z. We were told that 1 plus I is a root, so we can just stick it in there. Then we have 3 minus 2I times 1 plus I, and then we have plus p is equal to 0. So we have everything in there except p, so we should be able to isolate p. So let's do that. So we have 1 plus I squared, so that's going to be 1 plus 2I plus I squared plus 3 plus 3I minus 2I minus 2I squared plus p is equal to 0. Let's add everything up here. Let's see, we have a minus 2i, a plus 2i, and a minus 2i here. We have an I squared here, which is minus 1, and a plus 1 here. So that leaves us with this 3 here. And this here is actually a plus 2, because this I squared is minus 1, so minus 1 times minus 2 is plus 2. So 3 plus 2, 5. We also have this plus 3i here. No other i's there, so that's okay. We have plus p is equal to 0, and finally then that'll give p is equal to minus 5 minus 3i. So that's our answer, and I think that's what we got up here. Minus 5 minus 3i, yep, that's what we got here. Okay, so that's it for part A. Let's have a look at part B then. Use the Moivre's theorem to find the value of omega here, where omega squared is equal to minus 1 plus root 3i. Give each value of omega in the form a plus bi, where a and b are elements of OR. Okay, so again, this is a standard procedure. We have our w here, or omega if you like, is equal to minus 1 plus root 3i. Now the first thing we've got to do is convert this into polar form, or general polar form even in this case. So if we have a look at that, we have our Argand diagram here, a complex plane, and we know that it's going to be here somewhere. We've got to go out negative here on the real axis, and then positive on the imaginary axis here. So there's our complex number there, minus 1 plus root 3i. So we're coming out here 1, or minus 1 if you like, but the distance is actually 1. And up along here, root 3. Now, we need to work out a couple of things here. We need to work out this angle here, the argument, which is theta. And in order to do that, we're going to work out the reference angle here, which is alpha. The other thing we need is the modulus here, the distance from the origin. So let's do those things. So let's look at the modulus of omega squared first. So that's going to be the square root of minus 1 squared plus root 3 squared. If you do that, you get minus 1 squared is 1, root 3 squared is 3, 3 plus 1 is 4, the square root of 4, 2. Okay, so that's it. Now we need to work out the angle theta now. Okay, in order to do that, we're going to use the reference angle here, alpha. So to do that, we're going to have a look at the tan of alpha. The tan of alpha is root 3 over 1, or just root 3. So tan inverse root 3 is going to give us our alpha, and that will give us, if you look that up in your tables there, you'll see that the tan of 60 degrees is root 3, the tan of 60 degrees. Now I'm going to use radians here, so that's pi over 3. You can use degrees either. I'm going to use radians. Now this is our alpha, our reference angle. So I need theta, so our theta then, our angle is going to be, let's see, it's going to be 2 pi over 3. 2 pi over 3, or 120 degrees. 2 pi over 3, I got that because from here to here, 180 degrees is pi. Pi is just 3 pi over 3. We've got to go back 1 pi over 3, so that gives me 2 pi over 3. Okay, so we have everything we need now to write this in polar form. So our omega squared, or w squared here, is going to be equal to 2 cos 2 pi over 3 plus 2n pi plus I sine 2 pi over 3 plus 2n pi. Okay, now if you use degrees here, this would be 120 degrees plus, you need to take 360 degrees, that's our 2 pi, and multiply that by n. So that's what you would be writing in here, 120 degrees plus 360 n. I'm just going to stick with radians for the moment anyway. Okay, so now we've got to use the Moivre's theorem. So let's see, we're going to take omega. So we're going to get the square root of both sides. So I'm going to take our 2 cos 2 pi over 3 plus 2n pi plus I sine 2 pi over 3 plus 2n pi. And let me see, I've got to raise that to the power of a half, getting the square root of both sides. So here's where we're using the Moivre's theorem. So our omega here, our w here is going to be equal to, what we've really got to do now is take the half and use the Moivre's theorem. So we're going to bring it down here, we're going to bring it in here, and we're going to bring it down in here as well. So let's do that. First of all, we've got 2 to the power of a half, which is just square root 2. Now I've got the cos of a half of all of this here. So that's going to be the cos of, if I get a half of 2 pi over 3, that's just going to be pi over 3. If I get half of 2n pi, that's just going to be n pi. Same over here, so I've got I sine, and if I put a half in here, the 2's will cancel and I'll just end up with pi over 3 plus, and again the 2's will cancel here and I'll get n pi. So this is what I'm going to be working with now. Okay, so we're going to start here with n is equal to 0. So we're going to start with n is equal to 0. So if n is equal to 0, my first root here, we'll call it z1, let's say. Put n is equal to 0 here, that'll give me the square root of 2 times cos pi over 3 plus I sine pi over 3. That's it. Let's just convert that to rectangular form. So we've got square root of 2 here. The cos of 60 degrees, the cos of pi over 3 is a half, and the sine of 60 degrees is root 3 over 2. So let's just simplify that then. We get root 2 over 2 plus I times root 2 times root 3 is root 6 over 2. We could probably just write that as root 6 over 2i. So there's my first solution when n is equal to 0. Root 2 over 2 plus root 6 over 2i, that's in the first quadrant. So our second solution, because there are only two solutions, our second solution should be minus and minus here. It should be in the third quadrant, 180 degrees from that. So let's do that. We have n is equal to 1. So let's do that. So remember, we are using this here. This is what we're using. So we've got our second root here. Our second root is going to be square root of 2 times the cos of pi over 3 plus pi, because remember n here is 1 now, so plus I sine pi over 3 plus pi. So you have a root 2 here. Now here we've really got cos pi over 3 plus pi. And remember, pi can be just written as 3 pi over 3. 3's will cancel here, just give me pi. So I have 3 pi over 3 plus 1 pi over 3, so that's just 4 pi over 3. Plus I sine 4 pi over 3 here as well. Okay, so let's just convert that to rectangular form. So we have square root of 2. Now we want the cos of 4 pi over 3. So if you think about that, 4 pi over 3, where is that? Well, 3 pi over 3 is pi, and remember pi is here. This is just 3 pi over 3. This is 3 pi over 3, which is pi. We want 4 pi over 3. 4 pi over 3 is another pi over 3 down here. So in other words, my reference angle here is just pi over 3. This is 4 pi over 3 from here to here. This is 4 pi over 3. So all I've got to do is find the cos and the sine of pi over 3, and then have a look at the signs after that. So let's do that. So the we need the cos of our reference angle here, the cos of pi over 3. The cos of pi over 3 is a half. So our answer is going to be a half anyway. But we're in the third quadrant, and cos is negative in the third quadrant, so it's going to be minus a half. You can see here it's going to be minus minus anyway, but let's just run through it step by step. So that's our cos 4 pi over 3, and then we have plus I. The sine of 4 pi over 3 is going to be the same as the sine of pi over 3, our reference angle. The sine of pi over 3 is root 3 over 2. So this is just going to be root 3 over 2 here. It's in the third quadrant. Sine is negative in the third quadrant. So this here needs to be a minus. And that's it. Now let's see. We've got minus root 2 over 2. And then minus root 6 over 2i. So that's my second solution. So if my first solution was up here, and the second solution 180 degrees from it, which was here. So this is my Z1 and this is my Z2 here. We didn't have to plot it, but that's just showing you where it is. Okay, I think that's all we had to do for that question. Let's just have a look. Use the Moivre's theorem to find the values of omega. So for which omega squared is equal to minus 1 plus root 3i. So it's a quadratic, so there are two solutions. Okay, perfect. Let's have a look at the next question then. C. The Argand diagram below shows the complex number u is equal to a plus bi, where a and b are real. So that's it here. Okay. Write the complex numbers iu and the complex conjugate of iu in their simplest form in terms of a and b, where iu is the complex conjugate of iu. Okay. So we have u here is equal to a plus bi. We want I times u. So that's going to be ai plus bi squared when you multiply each of those by I. So our iu is going to be, this here is minus 1, so that's minus b plus ai. Okay, so that's the first answer there, okay, and then it says we need the complex conjugate of iu, so that means then that iu conjugate is going to be minus b minus ai. Okay, so that's really part 1 done. Part 2 then says plot and label the complex numbers iu and the conjugate iu on the diagram above as accurately as possible. Okay, so let's do that. So let's see, we have iu is equal to minus b plus ai, minus b plus ai. Now this here is a, which means we go out as far as here a, and then we go up as far as here b. So b is this distance here, so let's go out along this distance here. Because it's minus b, so I'm going to say minus b is going to be around here somewhere. And then we want to go up a. Remember, a is only that little distance there, so that's going to be around here. So this is where my first point is going to be. This is iu. So this is iu. And you can see that that's really just simply a rotation of u 90 degrees anti-clockwise around about the origin. When you multiply something by, when you multiply a complex number by I, it's a rotation, anti-clockwise 90 degrees. Okay, so that's the first one. We've also now got to plot the conjugate of this particular value here, this particular complex number here. So that's going to be minus b minus ai. So that's just going to be down, that's just going to be down here. So this is iu conjugate. So it's really just the same distance down here. I haven't got it plotted very well here. That distance will be the same as that distance here. The minus b here is in the way here. So that's it. Plot and label the complex numbers iu and iu conjugate on the diagram above as accurately as possible. So that's really it. That's iu there, and that's iu conjugate here. Now, state a transformation or series of transformations that would send u to iu conjugate, do not include a translation in your answer. Okay, so let's write all that out. So first thing we've got to do is firstly rotate U anti-clockwise anti-clockwise 90 degrees about the origin, or about 0 plus 0I, and then reflect using, let's say, axial symmetry. In the real axis. So I think that's it. Firstly, you rotate U anti-clockwise 90 degrees about the origin, then reflect that point in the real axis using axial symmetry. And that should do it for us, I think. State a transformation or series of transformations that would send U to IU. Yeah, that would be it. Okay, so that's really it for this question.